Okay, last class we have discussed graphical method, how to solve a linear programming problem using graphical method if it involves only two variables. Okay, we have two methods. First one is we draw the cost function and straight lines parallel to cost function, then find the vertices passing through this cost function, then we can evaluate maximum and minimum. Otherwise, you just identify all the vertices of the region and find the solve for these vertices and check whether what are the values of the cost function on these vertices. Then we can identify which one is minimum, which one is maximum. That is due to this result. Okay, if LPPN has optimum, then it must occur at a vertex. Okay, on the set of feasible solution. And we have seen, yeah, this example. And the another one is find the maximum of z is equal to 5x1 plus 8x2 subject to these two constraints. So first of all, we have to find the set of all feasible solution by drawing the straight lines. And here origin satisfies this side. Okay, so the common region means the region bounded by these two constraints, and this non-negative restriction is this orange shaded region. So for solving the maximum and minimum, either you solve the vertices. Here the vertices are, this one is 0, 5, and this one is 9 by 4, 15 by 4. By solving these two straight lines, we get this vertex, and this vertex is 6, 0. Okay, this is 0, 0. Okay, that theoretically says that the maximum and minimum occur only at vertices for a feasible region. Okay, so what is our objective function? Our objective function is z equal to 5x1 plus 8x2. So next you simply evaluate what is the value of this objective function on these vertices. Okay, then you can easily pick which one is maximum or which one is minimum. You take you draw a table like this, and here the vertex, here the value of z. Okay, so we have only 4 vertices for this feasible region. So first one is 0, 0, other one is 0, 5, next one is 9 by 4, 15 by 4, and we have one more vertex, that is 6, 0. Then evaluate what is the value of z on these vertices. So at 0, 0 its value is 0, at 0, 5 its value is 40, and at this point value is actually 41.25. yes, this is 41.25, and at 6, 0, 30. Okay, from this table it is clear that the maximum value at this vertex, so this is the maximum. Okay, we know that theoretically maximum occur only on the boundary. Okay, not inside, which is bounded. Okay, so here the maximum of this function occurred at 9 by 4, 15 by 4, and its maximum value is 41.25. And similarly, what is the minimum? What is the minimum of this function? Okay, that is also from this table. From this table, we know that theoretically maximum and minimum both occurred only on the boundary points, vertex. Okay, so here from this table, it is clear that the minimum value of z is 0 at origin. Okay, minimum value at 0, minimum value 0 at origin. Okay, you can also find this optimum using our by drawing cost function. For example, you can draw a cost function 5x1 plus 8x2 equal to 0. Okay, then what about the straight line? This is almost like this. This is x1, x2. When x1 equal to 0, x2 also 0. This is passing through origin. And when x1 equal to some 1, then what about x2? x2 equal to almost minus 5, 8, right? Isn't it? Minus 5, 8. Minus 5, 8 is anyway less than 1 quantity. So what about the straight line? The straight line is like this, passing through origin, and when x1 equal to 1, x2 equal to somewhere here, it is minus 5 8, which is less than 1, so somewhere here. So anyway, this is the straight line. So this is the straight line is like this, almost like this. So we know that the value of the function, value of the cost function on the straight line and on the straight line is constant. Okay, similarly you consider another straight line parallel to this cost function, then value of the objective function is constant throughout this straight line. Okay, it is clear that it is moving like this, then it passing through this vertex. ഇതിലൂടെ pass out. Okay, so it is clear that this iso-cost line, such lines are called iso-cost line. Okay, because cost function is constant on such straight lines. Okay, so this iso-cost line pass through this vertex and this vertex. So one of them is maximum, other one is minimum. Okay, അപ്പോൾ അത് കണ്ടുപിടിക്കാൻ വേണ്ടി you simply solve these two vertices and find the value of z. That's all. Anyway, this is the idea, and we have one more problem. Suppose you consider this problem, find the maximum and minimum of z is equal to 4x1 plus 4x1 plus 2x2 subject to these constraints. So first we have to find the feasible region by drawing these straight lines, and you identify which region is left or right. And after drawing all the straight lines, and this orange region is the feasible region. Okay, you draw each straight line and identify which region is feasible. Okay, so here this is the region bounded by these three straight lines. Okay, and this is an infinite region. Actually this is like infinite, it's an infinite region. Okay, this is an infinite region. Actually this region is unbounded. Okay, so how to find its maximum and minimum? Again you can apply one technique. Either you can solve these vertices. Okay, here this vertex is 1 4, this is 2 1, this is 4 0. Then you evaluate what is the value of the function on these vertices. Okay, so at 1 4, what is the value? At 1 4 its value is 12. At 2 1 its value is 10. Z value is 10. This is our result. Objective function is 4x1 plus 2x2. So you can substitute x1 and x2 on this z. Okay, so z is 10 at this vertex, z equal to 12 on 1 at 1 4, z equal to 10 at 2 1, and here its value is 16. Z is 16. Okay, from these three vertices, actually this region is not bounded. Okay, this is not bounded. Okay, so from these three vertices it is clear that 10 is the minimum. Okay, but there are values which are greater than 10. So that is the indication that this function, this objective function is unbounded on this region. Okay, കാരണം that result is true for only bounded region. Okay, if a feasible region is bounded, the theorem says that if the feasible region is bounded, then its maximum and minimum occurred only on the vertices. Okay, actually here the region is not bounded, it is unbounded region, so there is no guarantee about maximum and minimum. But from this observation it is clear that the least one is 10, so the minimum value of the function is 10. No, that is true. Okay, but we can't say anything about what is the maximum of this function. Okay, അതിനെക്കുറിച്ച് നമുക്കൊന്നും പറയാൻ പറ്റത്തില്ല. അതുപോലെ തന്നെ you can observe this concept using our iso-cost straight lines. Okay, here what about our cost function? Suppose you draw a straight line, like suppose you consider a straight line. Okay, suppose you consider straight line like this, 4x1 plus 2x2 equal to 0. It's a one iso-cost line. Here the cost is 0. Okay, so what about x1 and x2? When x1 is 0, x2 also 0. When x1 equal to 1, x2 become minus 2, right? So you can draw the straight line, so passing through 0 0, and when x1 equal to 1 is its value is somewhere here, minus 2, x2 is minus 2. So straight line is almost like this. Okay, then you move the straight line to this side. You can move the straight line to this side like this, parallel to the straight line. then it is clear that it is passing through this vertex. So this vertex may be minimum or maximum. Okay, again, if you move the straight line, then what happened? The cost function is different on the straight lines, and it is clear that when cost function hit this point, its cost value is 12. So it is an indication that when we move the straight line on this direction, its cost value is increasing, indefinitely increasing. Clear? That is an indication that here this function is unbounded in this function is unbounded, and but it is bounded below by the value z equal to 10. Okay, so you can identify this you can solve this problem either using iso cost line or by solving the vertices. Okay, since this is an unbounded region. So here this function has no maximum, this function has no maximum, but it has a minimum at 2 1 and its minimum value is 10. You got it? Graphical method if the region is bounded, then you can easily solve. You simply find the vertices and find which one is maximum, which one is minimum. That's all. If the region is unbounded, then namukadu observe cheyanam. You solve the vertices and from the here it is 10, 12 and 16. So it is an indication that this function is bounded below by 10. That is an indication. Okay. Otherwise, you draw a isocost line, then move the straight line to the feasible region, in the direction of feasible region. Then you can check whether the this function is unbounded or bounded, below or above. Okay. So this is the idea about graphical method. Next we are going to discuss here if the number of variables is if number of variables are 2, then only we can apply the graphical method. If number of variables is 10, what we will do? We can't apply the graphical method. So for that we will develop a general method, that is called Simplex method. So using Simplex method, you can solve any general LPP. Whatever be the number of variables, you can solve the general LPP using Simplex method. Okay. So before going to the Simplex method, first we have to identify what is the standard form of an LPP. Okay, we will apply the Simplex method on the standard form of the LPP. Okay, not in the given form of the LPP. So first of all, we are going to discuss how to write the standard form of a given LPP. Okay, this is the first restriction. All the constraints should be expressed as equations by adding slack or surplus variables. That means, for example, suppose our constraint is x1 minus 2x2 is less than or equal to 7. Other constraint is x1 plus x2 is greater than or equal to some 9. Okay, then our aim is to convert all the constraints as equations. We have to convert all the constraints as equations. So how to convert this inequation to equation? It is clear that left hand side is some less than some 7. Okay, so by adding a quantity, so x1 minus 2x2 plus something become 7. Clear? That's idea. Such variables are called slack variables. Okay, so if LHS is less than type, then we can add something to create an equation. Okay, to get an equation. Okay, so such variables are called slack variables. Here the left hand side is greater than 9. Then what happened? We have to find an equation. So to get an equation, we have to subtract something. That means x1 plus x2 minus a positive quantity. Minus a positive quantity become 9. That's the idea of surplus variable. So it is clear that here s1 and s2 both are positive. Clear? Here both are positive. Because in the first case we add something, in second case we subtract something. So this s2 is positive and s1 is also positive. Such variables are called slack and surplus variable. Okay. Then the next one is the RHS of each constraint should be non-negative. RHS should be non-negative. Very clear. The objective function should be maximization type. Objective function maximization type ആയിരിക്കണം. Otherwise we will convert, suppose objective function is minimization type, then that is not in standard form. So we will convert that minimization problem to maximization problem, then only we will get a standard form. Okay, so how to convert minimization to maximization? If the problem is minimization type, then convert it to maximum of minus z. Okay, why maximum of minus z? Because suppose we have to find suppose this is 0, suppose our function is like this, our objective function z is like this is our 1, our objective function starting from 1 to infinity. Suppose our objective function is unbounded and its lower value is 1. So minimum of z is, in this case minimum of z is 1. You got it? Then you consider minus z. This is the range of z. Then what about minus z? What is the range of minus z? Z is varying from 1 to infinity. Then what about the range of minus z? If z is varying from 1 to infinity, then what about range of its negative?
Minus infinity.
Minus infinity to minus 1. Yes. So this is the range of minus z. Okay. Next, our aim is to identify this one. You got it? Our aim is to identify this one using maximization problem. Okay. Okay. Then what about maximum? Then how to get this one? Then how to find this one? We consider maximum of, is it 1? Maximum of minus 1 is 1.
Minus 1.
Yeah, that is minus 1. So we consider minus of maximum minus z. You got it? So this one means this is nothing, this is minimum of z. So we can write the minimum of z as minus maximum of minus z. Here we denote the minus z as z star. Okay, so you can convert every minimization problem as a maximization problem. Okay, instead of minimizing z, you can maximize minus z, then ultimately you put a minus sign to get the minimum value. You got the idea? Because maximum of minus z gives only minus 1. We have to find the minimum of z. To get the minimum, you take a minus 1. So that's the idea. So if we can convert every minimization problem as a maximization problem using the relation maximum of minus z. Okay, first we if we maximize this function, suppose maximum value is some L, then to find the minimum you consider minus L. Then minus L is the minimum of Z. You got it? That's the idea. Okay, next one is suppose xi. One variable is, some variables are unrestricted in sign. Unrestricted in sign means we have non-negative restrictions. That means x1 is greater than or equal to 0, x2 is greater than or equal to 0. Such restrictions are called non-negative restriction. Okay, in sometimes some variables have no restriction. It may be whatever be the real number. X1 may be x1 can take any real value. Okay, in such situation, here we say that x1 is unrestricted in sign. You got the idea? So it's only a technical term. Suppose x1 is unrestricted in sign. Unrestricted means x1 has no restriction. X1 can take any real value. That means maybe positive or negative, 0, whatever, no problem. But this means x's are restricted. They must be non-negative. You got it? So when a variable is unrestricted in sign means meaning is meaning is x1 can take any real value. That's all. Okay. Then our aim is to convert. The LPP involved, or LPP should involve only non-negative variables. Okay. Then how to convert x1? Actually here x1 can take any real number. So we are going to replace this x1 using non-negative variables. Okay, that is possible because every real number can be written as difference of two positive real numbers. You got it? For example, 10. We can write 10 as 20 minus 10. So every real number is a difference of two positive real numbers. Suppose minus 10. then we can write this minus 10 as a difference of two positive real numbers. What is x1 dash and what is x1 double dash in the case of minus 10? Can you give a pair? Suppose x1 is minus 10, it's a negative number. How to represent this minus 10 as a difference of two positive numbers?
10 minus 20.
10 minus 20. So here this is our x1 dash and this 20 is our x1 double dash. You got it? So every real number can be written as difference of two non-negative numbers. That is possible. Okay, so if some variables are unrestricted in sign, then we have to convert that variable in terms of non-negative variables by substituting xi by xi dash minus xi double dash. You got it? Okay, that's the idea. So to write the standard form, we have to convert all the unrestricted variable as restricted variable by suitable substitution. Okay, so these are the conditions for standard LPP. So a standard LPP should satisfy all these conditions. All the inequations should be equations by adding slack and surplus variables. Right hand side should be non-negative and objective function should be maximization type. If it is not maximization, then we will convert it into a maximization type. And all the variables are non-negative. All the variables should non-negative. Otherwise, suppose some variables are unrestricted in sign, then we have to convert such variables in terms of non-negative variables by substituting xi by xi dash minus xi double dash. That's all. Okay, so we have to see an example. So transform the following LPP into standard form. Minimum of z is equal to minus 2x1 plus 3x2 subject to these two constraints. And here x1 is unrestricted and these two variables are restricted. They are non-negative variables. Okay, so it involves all the procedures in this algorithm. So how to find the standard form of LPP? First of all, we have to convert this minimization to maximization. So what is the corresponding maximization problem? What is the corresponding maximization problem? Maximum of z star. What is our z star?
2x minus.
Yeah, so the problem is like this. Maximum of maximize z star. Z star means minus times z, that is 2x1 minus 3x2. So we have to maximize this function. Okay, then next we have to convert all the inequations to equations. But we have one more condition. RHS of each constraint should be non-negative. Okay, so what about this equation? What is the equation corresponding to this inequation? We have to add slack or surplus variable to convert this as an equation.
Surplus. Slack.
Yeah, slack variable, because it's already less than or equal to, so we have to add something on the left hand side. So the equation corresponding to this inequation is x1 minus 3x2 plus 2x3 plus s1 equal to 3. Okay, and what about this one? Is it in standard form?
No, RHS.
Yeah, here RHS is negative. So first we have to convert RHS as positive. Then only we can add slack or surplus. Okay, so first we multiply with minus 1. So this inequation become minus x1 plus 2x2 greater than or equal to 2. Then we can add slack or surplus. So it is clear that it is left hand side is greater than. So to get an equation, we have to subtract something from the LHS. So that is called the surplus variable. So the equation corresponding to the second inequation is minus x1 plus 2x2 minus s2 equal to 2. Okay, now we have two equations and this is our maximization problem. This is our maximization problem and these are the two equations. Then come to our variables. Yeah, we have an extra problem. x1 is unrestricted in sign. So we have to convert all the variables as non-negative variables. x2 and x3, okay, they are already restricted, they are already non-negative. So we don't bother about x2 and x3. So how to convert x1 to get a standard form of LPP? We have to replace all the x1 by, we have to replace x1 by difference of two non-negative variables. That is, we take the first one as x1 dash minus x1 double dash, because this means these two variables are from with for x1. That's why we use the lower suffix as x1. Okay, one means first variable, two means second variable. That's all. Okay, so also we assume that x1 dash comma x1 double dash are positive. This is possible because every real number can be written as difference of two non-negative number. That's the idea. Okay, so yes, so the problem become maximize z star equal to like this, and we add one slack and surplus, and now we have an unrestricted variable x1. Then next we are going to substitute, we are going to replace x1 by difference of two non-negative variables. That means we are going to replace x1 as x1 dash minus x1 double dash, and also we assume that x1 dash comma x1 dash double dash are greater than or equal to 0. They are non-negative. Okay, so now we have the standard form. This is the standard form of that given LPP. Now everything is okay. The problem is maximization type. All the inequations are equations, and right hand side are non-negative, and now all the variables are unrestricted. All the variables are non-negative. S1 is positive, S2 is positive. They are already given, they are non-negative, and we introduce new variables, they are also non-negative. You got it? So this is the standard form of LPP. We can solve these type of LPPs using simplex method. We can solve this type of LPPs with the simplex method. Okay, so next we are going to see how to solve a standard LPP using a simplex method. How to solve a standard LPP using a simplex method. There is one more question. Suppose in this case, maximum of z star, suppose that is equal to minus 3. Then what is the minimum? What is the minimum of our z? Suppose maximum z star equal to minus 3. After some calculation, we have maximum z star equal to minus 3. Then my question, what is the minimum of z?
3.
That is 3. That is minus of maximum of z star. The idea. Okay, the point remains same. The optimum point has no change. Okay, similarly, suppose after some iteration, suppose we have like this, the maximum z star is minus 3, occurred at like this. Suppose x1 equal to, suppose x1 dash equal to some 5, and x1 double dash equal to 1, and x2 equal to 3. Okay, suppose this is the situation. After iteration, we have like this, maximum of z star equal to minus 3 at x1 dash equal to 5, x1 double dash equal to 1, x2 equal to 3. All the variables are non-negative. So what is the value of x1 and what is the value of x2? Actually, our decision variables are x1 and x2. You got it? In our actual problem, or sorry, x1 and x2 and x3. Suppose x3 equal to 0. Leave it. Then what is the value of x1 and what is the value of x2? Suppose x3 equal to 0. And what about x1? x2 is okay, 3. What about x1?
Minus 4.
Yeah, x1 is no, x1 is x1 dash minus x1 double dash. Okay, here x1 dash is 5, x1 double dash is 1, so it is 5 minus 1, that is 4. So x1 is 4. Okay, suppose it is like this. Suppose it is like this. This is 1 and this is 5. Then what happened? Then x1 dash minus x1 double dash, that is our x1. x1 is minus 4. You got it? So here our variables are non-negative, but our actual decision variable is negative. This is possible because as x1 is unrestricted in sign. So x1 may be negative. Okay, that's the idea. Okay, so how to solve a problem? Suppose we have a standard LPP, then how to solve the standard LPP using simplex method? Okay, so first we have to set the initial simplex table. Okay, how to write the initial simplex table? Before moving to the simplex method, this is an important note. This method is applicable only when the standard form of LPP contains only slack variables. That is very important. Okay, first, after conversion, if standard form contains only slack variables, then only you can apply this simplex method. Otherwise, you can't. Okay. In our previous problem, you can I think you can't apply simplex method. And, in this problem, you can't apply the simplex method because in this standard form, it involves a surplus variable. It involves a surplus variable. This is a standard form, but the standard form contains a surplus variable. So we can't apply LP simplex method. Okay, we can solve this problem using simplex method. Okay, so anyway, if the after conversion, if the standard form contains only slack variables, then we can apply the simplex method. So this is the initial simplex table. And how to find the initial simplex table? To get the initial simplex table, suppose we have constraints like this: some x1 plus s1 equal to some 7, some x1 etc plus some s2 equal to 5, like that. Okay, initially we take these slack variables are basic. Okay, initially we take slack variables are basic. All the slack variables are basic. So automatically our other variables are non-basic. Got it? Other variables are non-basic. Other variables means actually our decision variables. Our decision variables are non-basic. And we know that when we solve an equation with the basic and non-basic, we treating all the non-basic variables are 0. If we solve the system with the basic and non-basic concept, at that time we will treat all the non-basic variables are 0. Okay, so first of all we are going to set all the decision variables are 0. If all the decision variables are 0, then what happened? Then from the first equation we get s1 equal to 7, from second equation s2 equal to 5, like that. Okay, so here this is the value of the basic variable. You got it? And this is this column is represented basic variable. This is the value of the basic variable. This is the cost of the corresponding basic variable. You got it? So in the initial table, the value of the s1 always b1 and this is always b2, because we set all other variables are 0, all the decision variables are 0. Okay, so initial simplex table is like that. So suppose our problem is like this: maximize some C transpose x subject to a x is equal to b. Then we know that what is b? B contains b1, b2, bm. Okay, they are the values b1, b2, bm. And what is a? A is a matrix aij. So this is the matrix aij. Okay, this is the matrix aij. Okay, then here the coefficient of s1 in the first equation is 1, because the coefficient of s1 is 1 in the first equation. Actually the first row is corresponding to the first equation, that's all. The first row is corresponding to first equation and the second row is corresponding to second equation. Okay, on the second equation the value of s1 is 0 and value of s2 is 1, like that. Okay, so you can easily write this initial simplex table. Okay, and this is the value of basic. These are the basic variables. These are the value of the basic variable. These are the corresponding cost. What is the cost of the basic variable initially? What is the cost? So for example, okay, for example, suppose this is the situation. Then we have to maximize this problem subject to this condition. Okay, it is clear that in this cost function there is no s1, no s2. Okay, that means what? That means what is the cost of S1? The cost of S1 is 0, and similarly the cost of S2 is 0. Okay, so the cost of slack or surplus variable, whatever be the variable, their costs are always 0. Okay, in the case of simplex method, we have only slack variables and its cost is 0. Then only the problem remains same. Okay, this problem involves extra variables, but we set their cost is 0 because otherwise the maximum of the function is different. Okay, that's why we set the cost are 0. അത് ഈ എക്സ്ട്രാ കൊണ്ടുവരുന്ന വേരിയബിൾസിന്റെ എഫക്റ്റ് നമ്മുടെ ഒബ്ജക്റ്റീവ് ഫംഗ്ഷനിൽ വരാണ്ടിരിക്കാനായിട്ട് we have to set their cost 0. Okay, so that's why I'm saying initially these coefficients are 0. These are the cost. Okay, initially basic variables are or slack variables, their costs are 0 initially. Okay, then okay, another one is this values, this red values. How to find this red value? This is the formula of red values. How to find this red value? They are called ZJs. This is called Z1, Z2, etc. like that. They are called ZJs. Then how to compute ZJ? ZJ is evaluated using this formula, sigma CBI Aij. That is easy. CBI means this cost column. You simply think about this cost column. This cost column into respective column. Okay, in this case, suppose we are going to find what is Z1. Z1 means Z1 is corresponding to X1. So how to find Z1? You take the first cost multiplied with the first entry in this column plus second cost into second entry in this column, like that. Okay, that's why sigma CBI Aij. Okay, that is the value of Z1. Similarly, you can calculate Z2. Okay, this cost is remain same, column is different with respect to the variable. Okay, so you can evaluate Z1, Z2, etc. Okay, initially all the ZJs are 0 because initially this cost is always 0. You got it, because the cost are the costs of slack variable. We know that cost of slack variables are 0. So initially this column is throughout 0. So all the ZJs are 0 initially. Okay, then the last row, what is last row? Last row is Zj minus Zj. Cj's are there already. We have Cj's. What is the cost of x1? Suppose we have a problem like this: maximum z is equal to 2x1 plus 2x1 plus 3x2. Then here 2 is our c1. You got it. 2 is our c1, and c2 means second cost of x2, that is 3. You got it. So we know what are the cost of each variables, x1, x2, xn. Here they are the decision variables, they are the slack variables. We know that cost of slack variables are 0. That's why here we put zeros. Okay, this row is never changed because they are the cost of the variables, that is throughout same in all iterations. There is no change in the cost. Okay, so now you know this is the initial simplex table. So in initial simplex table, first you set this table, then you evaluate ZJs and Zj minus ZJs. Okay, then we have to move on the second table. The algorithm is, okay, so calculate Zj minus Zj for all non-basic variables. Cj minus Zj equal to 0 for basic variable. Okay, you can use this advantage. That means when we calculate this row, the guarantee is that for a basic variable, now they are the basic. In presently, these slack variables are basic. For the basic variables, this Zj minus Zj are always 0. So we no need to calculate that. You simply substitute 0. But we have to calculate Zj minus Zj for non-basic variable. Non-basic variable means variables other than these variables. Whatever be the variables in the second column, the variables other than variables in the second columns are the non-basic variable. So in the initial simplex table, the decision variables are non-basic variables. So we have to calculate Cj minus Zj for these non-basic variables. Okay. This is always true. Cj minus Zj is always 0 for basic variables. So anyway, we have to calculate Cj minus Zj for non-basic variables. Then second step, If all zj minus zj is negative, less than or equal to 0, then the present solution is optimal. Okay. After computation, we have to check whether all zj minus zj are less than or equal to 0. If it is like this, then whatever be the values of the variable presently, that is the optimum solution. Otherwise, if at least one ck minus zk is positive, at least one zj minus ck minus zk is positive, and at least one aik is positive, then further improvement is possible. This means, okay, aik stands for any entry in the corresponding column. That's all. Aik means this entry is fixed. Okay, so aik stands for any entry in the kth corresponding kth variable. That's all. Okay, so for example, consider this table. So we evaluate this cj minus zj. Suppose at least one. Suppose this one is greater than or equal to 0. Suppose z1 minus z1 is positive. Then we have to check whether what about the sign of this column. What about the sign of this column? Okay, if at least one variable is greater than or equal to 0, then further improvement is possible. That is the idea. Okay, so if at least one zj minus zk is positive and at least one entry in the corresponding column is also positive, then further improvement is possible. That means we can improve the solution. That's the idea. Okay, so at least one zk minus zk is positive and at least one aik is positive. Aik is nothing. This is the column entries corresponding to this variable. That's all. Okay, the variable corresponding to maximum of zj minus zj and zj minus zj is positive will enter the matrix. Okay, that means now we have at least one positive. Okay, suppose we have some other positive cj minus zj is there. Then we have to find the maximum. We have to find the maximum of such cj minus zj's. Okay, if maximum occurred at here, then this variable enter the basis. That means presently this is a non-basic variable and its value 0. Okay, if the maximum is corresponding to x1, then x1 will enter the basis. That means we have to remove one variable from this from basic variable. Okay, so you got it. You got the idea. So you find the maximum of cj minus zj's and the variable corresponding to maximum will enter the basis. Next we have to find which one is leave the basis. You find the living variable. Okay, that column is called a key column. That column is called a key column. Next we have to find the key row. Key row means the living variable. To find the living variable, we have to calculate. നിങ്ങളുടെ സമയമായോ? ആ അല്ലേ, ഇവിടെ നിൽക്കട്ടെ, ഇതിന്റെ ബാക്കി അടുത്ത ദിവസം കണ്ടിന്യൂ ചെയ്യാം കേട്ടോ.